Picture this. Two colossal black holes slammed together more than 7 billion years ago. The cosmic bang is over in a heartbeat, yet the ripple in space-time, the gravitational wave, keeps on traveling until it quietly jiggles LIGO's detectors here on Earth. Now here's the weird part. When physicists replayed that jiggle, event name Gravitational Wave Event GW190521, they heard a tiny off-key note. Not static, not a hardware glitch, a faint but orderly wobble that just didn't belong. Think of it like hearing a whisper-sized saxophone hidden inside a rock anthem. You know the main guitar riff, you've matched it to every studio track you own, but suddenly there's this extra breathy tone sliding underneath. You can't unhear it, and you can't explain it away. First question, is that whisper real or just our ears playing tricks? Instead of building a brand new telescope, the team dove back into the raw data. They treated the wave the way a sound engineer treats a master tape, pulling back the obvious instruments and cranking up every hidden slider. And there it was again, a small, systematic twist in the rhythm. Peaks arriving a smidge too early, valleys lingering a hair too long. Too neat for random noise, but too subtle to trumpet as a discovery, at least not yet. So what could be nudging that wave? Two big suspects step into the spotlight. One, a cloak of dark matter wrapped around the merging black holes, tugging on the outgoing ripple. Two, our own math. Maybe the templates we use to decode the signal have tiny blind spots. If it's dark matter, we've caught the first gravitational fingerprint of the stuff that outweighs normal matter 5-to-1, yet hides from every telescope. If it's bad modeling, then relativity tests just got a mandatory upgrade. Here's how the search works. For every collision LIGO hears, theorists generate a monster playlist of predicted waveforms, millions of them, each with different masses, spins, and orbits. The real signal is compared, track by track, until one song matches best. This time, the scientists let the playlist include background singers, extra gravity from nearby material. When they did, the best fit track showed that tidy phase drift I mentioned. Translate that drift into plain English, and you get numbers that look a lot like dark matter halos theorists predicted years ago. Dense, compact, the kind that could lurk around black holes born in ancient, crowded neighborhoods of the universe. Important caveat, that drift doesn't reveal the actual ingredient list. Could be one exotic particle, a whole family, or even something wilder like ultralight fields. What it does say is this: whatever's there must clump tightly, pull mainly by gravity, and still dodge every other cosmic test we've thrown at dark matter. That single constraint slices away a mountain of wild ideas. Now, a lone data point is never enough. So the race is on to comb through every thunderous merger in LIGO's archive, and all the juicy ones still to come, looking for that same quiet twist. If it pops up again and again, especially in the loudest, heaviest events, the odds tilt sharply toward real phenomenon and away from data hiccup. Here's an analogy. Imagine an enormous music library mislabeled to include only the lead singer on each track. Somewhere in those songs, a bass player might be laying down a subtle groove. Overlay enough recordings and, if that same groove reappears in just the right spots, you'll know the bassist is real, not random creaks of the studio floor. Practically, researchers scan for phase drifts with matching shapes and timescales. Then they ask bigger questions. Do these drifts prefer mergers in crowded star clusters? Do they show up even in quiet cosmic suburbs? Are they smooth like fog or clumpy like popcorn? Each clue helps sketch the unseen landscape. If the hints harden into solid evidence, we're talking about a new kind of cartography. Every gravitational wave event becomes a core sample of its neighborhood, letting us map where invisible mass crowds together or thins out over cosmic history. That could explain why some galaxies burst into star-making frenzies while others sputter, or why certain regions fire off spectacular jets. Let that sink in. We'd be mapping the universe without light, watching the invisible through the tremors it leaves on space-time itself. So, where do we stand right now? Picture a detective holding one partial fingerprint. It looks promising, but you need a stack of matches to close the case. The next observing runs, and the next generation detectors with even sharper ears might deliver that stack. And when they do, every new black hole crash won't just test Einstein. It will double as a probe into the dark heart of the cosmos. Recap and takeaways. So here's what we covered today. 1. In the gravitational wave event GW190521, scientists heard a tiny, orderly phase drift, a possible sign of something extra tugging on spacetime. 2. The prime suspect is a halo of dark matter around the merging black holes, though small mismatches in our theoretical templates could also explain it. 3. By allowing extra gravitational influence in their models, researchers match the data better and outline strict rules any dark matter candidate must follow. 4. The community is now scanning past and future black hole mergers for similar drifts. A repeating pattern would turn a hunch into a brand new window on the unseen universe. Now, the empowering part. Every time you hear about a gravitational wave detection, remember, you're not just listening to cosmic fireworks. You might be eavesdropping on the secret architecture of the universe. The next ripple could carry the next clue. Stay tuned. I'm glad you joined me on this trip through hidden halos and cosmic baselines. Until next time, keep looking or listening into the dark.